All right, so um, last class we left off looking at, well, we finished the proof for the variance of mu hat in, or for the variance of mu tilde in the context of a simple random sample. And then we started to look at actual applications of those formula. So there were two parameters that we focused on Friday, which were mu and tau. So mu is the population mean and tau is the population total. In general, these estimation schemes follow very closely to what we would have seen at the first and second year level. Essentially in this class, what we're doing is focusing on confidence interval construction because our focus tends to be, or the focus is usually on constructing estimates for the population mean and not so much addressing questions about the population mean. So the confidence interval is the natural tool in this case because it is a range of values that are used to estimate, or it's a range that gives us an idea of where the true mean might actually be located or what the value of the true mean might be. And the same thing with the population total. Okay, so the big difference between our confidence interval construction procedure in the simple random sampling case versus what we would have seen beforehand is that we are now accounting for the fact that we are working with populations of finite size. So we have embedded within our standard error formula the finite population correction, which you can see, for example, right here on slide 33. So this is our FPC. And essentially what we do here is we check to see if this FPC is greater than or equal to 0.95 each time we go to construct our confidence interval. And if it is, then we can ignore it. And if it is not, then we would include it. And if you think back to the structure of a confidence interval based off of what we would have studied at the first and second year level, you'll notice that the formula here are actually exactly the same, except that we have this FPC included in our situation where we have finite populations and we are not ignoring that fact. Versus at the first, second year level, we essentially just assume that populations are always of a fine or of an infinite size. So this ratio would never be considered. But the formula, again, is effectively the exact same thing, except that we have this correction in place because, again, we are cognizant of the fact that we have a value for capital N and we should consider that in our calculation of the interval. Okay, so on slide 33, we have an example of computing an estimate for mu. Again, this is a direct application of the formula that we saw, that we derived earlier in the lecture set, or that were stated earlier in the lecture set. And we know from our previous work that mu tilde is unbiased for mu, and we know what the variance of mu hat is. So, or what the variance of mu tilde is, which allows us to assess the accuracy and precision of the estimator, or the precision. Again, I always forget which one is which. Okay. The second example we looked at was an estimation of tau. In this case, we found an estimate for tau, which is given on slide 36, and then we constructed the bound. You'll notice that the bound here is the margin of error for the confidence interval. So if we wanted to build the confidence interval here, we would simply add and subtract the bound to tau hat. So a very straightforward application in that sense, and a direct extension of what we saw when we considered an estimate for mu. The big differences here are just that we are multiplying the bound and our estimate by capital N, as the estimate for tau hat is capital N multiplied by mu hat. All right, so that's where we left off. Now what we're going to do is talk about a few different things before the end of today's lecture. We're going to talk about estimates for the proportion based off an SRS. We're going to talk about sample size calculation for a simple random sample. So how many observations should I sample in order to achieve a particular bound? And then we'll move into the systematic sampling stuff, and we'll see how far we get with that today. Just before we get into the next part, which is the sample size considerations, or sorry, we're going to also talk about something called the coefficient of variation. And I'll explain what that is momentarily, but it's another way to assess essentially the strength of our estimator based off of empirical information. But just before we get into that, a small note on this finite central limit theorem and whatnot. So in practice, as you might remember, we focused a lot on using or building confidence intervals and constructing hypothesis tests that use the t-value in place of the z-score. And this was attributed to the lack of population information. So if we didn't have the population variance or population standard deviation, we would typically replace our z-score with the t-value to, in some sense, protect us from this lack of information, but it also gave us more, it would give us larger confidence intervals in terms of length because the t-values are typically greater than the z-scores for low degrees of freedom. Okay, so we know that in general, the rule of thumb for the central limit theorem is that we need a sample size that is greater than or equal to 30. However, the truth is that the sample size you actually require to have the sampling distribution of the sample mean return to a shape or form a shape that is approximately normal varies with how far the population variable deviates from normality. So just as a side note, it might be interesting for you to consider another approximation for the sample size you might require when you are interested in achieving or when you are interested in determining how far away or how many observations you need to collect in order to achieve an approximately normal sampling distribution for the mean. So in 2000, Sujin et al., they proposed the following calculation to determine how many observations might be needed in order for the variable you are working with to be, in order for the sampling distribution of the mean that you are interested in estimating to return to normality. And that equation is given at the end of slide 37. Okay, so this is sort of just a little bit of food for thought that this idea or that this rule of thumb that we teach for the central limit theorem is really meant to be taken with a grain of salt. And you can run different studies and show that different shaped distributions, so population distributions, when sampling from those, you require varying sample sizes in order to return to normality. In some cases, if you have a very small deviation from normality in terms of the population distribution, you actually you don't need 30 observations in order for the sampling distribution to get back to normality. You could collect samples of size 5 or size 10, and you will see that the sampling distribution in those cases looks very normal. But in other cases, you can be extremely far from normality. So something that's really heavily skewed, for example, and you might require 50 to 75 observations in order to actually observe a sampling distribution that is approximately normal. So this in some sense is kind of like an open problem, right? Like what would be the appropriate general rule or formula to determine how many observations you actually need to collect for the sampling distribution of the sample mean to return to normality? Okay, and in this paper by Sujin et al. 2000, written by Sujin et al. In 2000, they suggest the following rule for determining how many observations we need to achieve normality. So you can see here we have population measurements, and here we have, again, yi minus mu tilde. So each of these parts could be estimated, for example, using sigma hat, and then this could be estimated using yi minus mu hat, for example. Okay, so we could do empirical studies to determine what this sample size might be for a given situation that we're interested in building a confidence interval for. All right. Okay, so the next statistic or estimator that I want to introduce to you guys is called the coefficient of variation. Effectively, what we can use the coefficient of variation for is to determine which estimator of mu would be the best based off of, well, it gives us a criteria to evaluate which estimator of mu would be the best. Okay, so the coefficient of variation from a mathematical definition takes the square root of the variance of our estimator, so the standard error of our estimator, and divides it by our estimate for the parameter of interest. Okay, so you can see here, for example, the coefficient of variation for mu tilde is equal to the square root of the variance of mu tilde over mu hat. And that gives us the square root of 1 over n minus capital N sigma hat over the square root of little n times mu hat. So it's very similar to our standard error formula for mu tilde, except we have mu hat in the denominator here. All right, so the coefficient of variation will always be greater than or equal to 0 by construction, okay? And we can say that an accurate estimate of mu, or an accurate estimate of mu, will have a coefficient of variation that's actually very close to 0. All right, so we would expect the coefficient of variation to be very small for good estimators, is the idea. Okay, so let's look at a quick example of the construction of said coefficient. So here we have the US government conducts a census of agriculture every 5 years, collecting data on all farms in the 50 states. The census of agriculture provides data on number of farms, the total acreage devoted to farms, farm size, yield of different crops, and a wide variety of other agricultural measures for each of the capital N equals 3,078 counties and county equivalents in the United States. A simple random sample without replacement of size 300 gave mu hat equals 297,897. And sigma hat is equal to 344,551.9. Compute the coefficient of variation for tau, or for tau tilde rather. All right, so let's sample. All right, so what do we have in this question? Well, we have our population size, which is capital N. Okay. We are told that we collected a simple random sample of size 300. We are given the estimate of mu based off of that simple random sample. And we are given the estimate of sigma based off of that simple random sample, which noticeably is very, very high. I mean, this estimate of sigma is actually larger than the population mean, so the dispersion in this data set is extremely large. Okay, actually, and the reason for that is because this is actually sigma hat squared, which makes way more sense because that value is way too big to just be the standard deviation. Okay, so this is our variation. All right, so from the previous slide, we know that the coefficient of variation for tau tilde, or for tau tilde here, is equal to the coefficient of variation for mu tilde. Okay. Okay, so this is going to be equal to the square root of 1 minus little n over capital N multiplied by sigma hat squared over n multiplied by mu hat. Oh, actually, one second. This should be on the outside. It's not very pretty. Okay. All right, so from this point, It's really just a game of plugging into the formula here. So we're gonna have 1 minus 300 over 3078 multiplied by 343,551.9 over 300 divided by 297,897. Okay. And this gives us 0.0. Actually, I'll just write it out so that you have the top. So that should give us 18,898.4344428 divided by 297,897. Okay. And that should give us 0.0634. Okay. All right, so a few notes about this value. We established on the previous slide that values close to 0 would represent precise estimates of the population quantity of interest. So in this case, we can see that our coefficient of variation for tau tilde is equal to 0.063 based off of the sample that we are working with. This would imply that our estimator for tau is quite precise. Okay, so we'll say is very precise or very accurate, sorry. Okay. Now, the issue here is sort of the same thing as when using a p-value without a significance level. Like, what does it, how small or how close to 0 do you actually have to be for the estimator to be considered the best estimator or a good estimator? So the real strength or value of the coefficient of variation in the context of how we are using it is when we can use it to compare across different estimators. So while this value does imply that our estimator is very accurate, because I think we can agree that 0.06 is quite close to 0, in order for us to establish what it would mean for this to maybe be the better estimator based off of the different samples, we would need to collect more information and consider more estimates for mu in this particular problem. Okay, so the coefficient of variation is, let's say, best utilized as a tool for comparing multiple measurements. So what I mean by that is simply under the assumption that we have maybe multiple samples from the same population, we can compute the coefficient of variation for each of those different samples, and then we can compare them. Or, as we will see a little bit later, once we start to develop different sampling strategies, we can actually use the coefficient of variation to compare estimators across different sampling strategies. Okay, so for example, we can use the coefficient of variation to compare estimators from different sampling strategies. So at this point, we've only talked about simple random sampling, but we're going to talk about systematic sampling, stratified sampling, cluster sampling. And from each of those different approaches, you will see that we end up with the same goal. So I've used stratified sampling and I want to estimate the population mean. I've used cluster sampling, I want to estimate the population mean. Well, given that I've used the stratified approach, is this a better approach than if I just did a simple random sample? And one of the ways that you could answer that question is by comparing the coefficient of variation for the stratified estimator to the coefficient of variation for the simple random sample estimator. And now we have a tool, and now what the CV becomes is a tool for saying, well, the SRS estimator is actually more accurate than the stratified estimator because its value is closer to 0. So that gives us some evidence that maybe SRS would be the better approach for estimating the population mean in the context of whatever the experiment is. So the real value of this CV, or this of the coefficient of variation, is as a tool for comparing estimators from different sampling strategies, or you could compare estimators within the same exercise. So we could collect maybe 10 samples for this particular problem and then compare the estimators across those 10 samples. But you would expect, if you were to collect 10 samples from the same population, that the majority of those estimator or those coefficients are going to be very close together. You know, for example, if you consider the problem that's on assignment 1, question 5, where we sample from the podcast population, if you repeat that process, say like 10,000 times, you'll actually notice that the estimates are quite close together, and the bound on those estimates is pretty small. It's about, you know, all the estimates are within about 2 of each other across that whole experiment. So you would expect the coefficients of variation to be quite close as well, but it would give you an idea of which sample was giving the most accurate estimate across all the different samples from that population. All right. Any questions about the CV? We will see more examples of this later as well. Once I start talking about stratified sampling, we'll start to see comparisons. Once we see cluster sampling, we'll start to see comparisons. But for now, that idea is kind of, just want to sort of plant that idea in your minds going forward so that you have a sense of where we can go with this particular tool. All right. So the next question that we might ask when we're working with simple random samples, or with simple random sampling without replacement, is what is the optimal sample size for a given problem of interest? And this idea really just boils down to, given a particular bound for a problem and some previous population estimates, or some previous parameter estimates, what is the ideal sample size for you know, having the bound on our estimate within a certain number of units. So to construct an estimator for sample size, we're essentially going to take the same idea that we saw back in the first or second year level, where we rearrange the bound on the margin of error to solve for sample size, to solve for little n. The only difference here is that we're now dealing with this finite population correction. So that makes the arrangement of the formula a little bit a little trickier than it was in the infinite population case. All right, so if we want to determine little n for an SRS based off of a population with size capital N, we can start off by writing the following. So first, we'll let little c equal the z-score. And this is for no other reason than just it makes writing, I don't have to write z alpha over 2 every single time, but you don't have to do this. It's just a quick definition to change things. Okay, and then we'll let capital B be the bound. Okay, and that just follows from what we have, the letter that I used when we did the tau estimate earlier. All right, so we have capital B is equal to little c multiplied by the square root 1 over little n times capital N sigma hat squared over little n. Okay, so C again is just the distribution value, so the z-score, or it could be a t-value. B is just a symbol used to represent the bound. You can actually use any letter you want in place of capital B. Okay, our goal here is to solve for little n. Okay, so there's a few different ways that you can go about doing this. This is the way that I typically have shown. So we can start by squaring both sides. And then what we can do is expand out our fraction here. So this is going to give us c squared times sigma hat squared over little n minus c squared times sigma hat squared over capital N. All right, and then we'll have b squared divided by c squared sigma hat squared, which is equal to 1 over little n minus 1 over capital N. Okay, and then we'll have little n is equal to b squared divided by c squared sigma hat squared plus. Okay. So as I said before, pretty similar idea to what we saw back in our earlier studies of how to compute sample size. And in fact, what you can see here is if capital N is really large, so if we're dealing with a population that has, well, let's say, it's hard to give a bound, but if you're dealing with a population where 1 over capital N is only going to add, say, 1.0 times e to the negative 5 or e to the negative 6 to the sample size approximation, you probably don't really need to deal with it, or you can ignore it, because at the end of the day, once we have actually computed the value of little n directly from the formula, we always tend to round up anyways, because we want to collect we want to collect the sample size that's going to make sure that we achieve our goal. So in general, once we have n from the formula, we always round up, because if we round down, we might miss the bound or miss the goal of the experiment. And due to that rounding, the 1 over capital N might not play a big role in the actual computation. So when n is large enough, it follows that we can write the required sample size for estimating mu using SRS as follows. So we have n, which is approximately equal to, and here we have z squared over sigma hat squared divided by L, we have z alpha over 2 times sigma hat divided by L all squared. So you can see that this is just the inverse of what is given above, but we're ignoring that 1 plus n factor. And again, it's due to the fact that we always round up after the calculation. So most often we're going to be able to get away with using this formula, but in some case, but it's not going to make a difference if we include the 1 over n. It's not like that's going to change the outcoming value, is the point. All right, so there's a few things that we need in order to estimate the sample size for the SRS. Obviously, we're going to need to specify a confidence level, because the z-score is going to be determined based off of the confidence level that we are using, right? So if it's a 95% CI, the z-score is 1.96. If it's a 90% CI, the z-score is 1.645. We also will need some estimate of sigma, or we will have to have population information in order to complete the formula. So usually based off of the sample we are working with, or a previous sample that we had access to, or previous studies that we had access to, we can make an educated guess at sigma hat. I'll show a couple examples of this momentarily. So for example, let's suppose that we wanted to estimate average diastolic blood pressure of the women in the PIMA study within 3 millimeters hemoglobin of the true value with 95% confidence. So what we're saying here is we want to place a bound of 3 on our estimate for mu. Okay. What are some of the possible sample, or what are the sample sizes if, for example, a previous experiment suggested that the variance would be 370.6284, or if previous experiments suggested that the range might be 846. So in this particular problem, we want to estimate mu. We want to estimate mu within a certain bound. We need an estimate of sigma squared, so of the population variance, in order to compute the bound. And one of the ways that we can get at this estimate is from previous experiments. So we have 2, let's say, different experiments, and one of them suggests a direct estimate for the variance. Another one suggests that the range of diastolic blood pressure in the population is about 846. So how can we work with that? Well, in the first case, okay, in the first case, we can just directly plug in here. So we're going to assume that n is large for this particular study. Again, in most cases, you're not going to need to include that factor of plus 1 over n, because we round at the end anyways. But just for completion's sake, we'll say assume n is large. And in fact, I think from a previous example, we were given, yeah, so n should be approximately 768 for this study. So we can actually show the effect of this for a comparison later. But let's assume n is large for now. All right, so we're going to have capital B is equal to 3. We're going to have sigma hat squared is equal to 370.6284. This should not have units on it. Okay, and then we will have Z 0.025 is equal to 1.96. Okay, so then little n is going to be equal to Z alpha over 2 multiplied by sigma hat squared Z over 2 squared multiplied by sigma hat squared divided by b squared. Okay, so this is going to be 1.96 squared multiplied by 370.6284 divided by 3 squared. Okay, and that should be 136.5918. Okay, so in this case, n is approximately, or we require n to be equal to 137. Okay. All right, now, just going back to my previous point, so recall that capital N for this experiment was 678. Okay. So this means that 1 over capital N is equal to 1 over 768, which is 0.00130. Okay. So had we added this factor to, or included this factor in our calculation, you can see that the result would have been that we were only adding 0.0013 before we inverted to get to our sample size. So the result here, if we were to compare them, is probably going to be minimal, and we would end up with the same solution anyways. So if we were to actually consider this value within the calculation, we can show from the formula that we derived earlier. One second here. So we would have had 3 divided by oh, 1 second. I had the wrong value there. So that should be 158.2007. Sorry about that. Make some updates. Okay. So then if we were to actually include that bound, let's see what the effect is. Oh, it's actually quite significant. So in this case, oh, I was wrong. Look at that. Okay, so if we include the bound, oh, look at that. Learned something new. Okay, so if we include the bound, then we have this additional factor to consider. So then we would have had little n is equal to b squared over z alpha over 2 squared multiplied by sigma hat squared plus 1 over capital N inverse. All right, so this would have been 3 squared over 1.96 squared, 370.6284. I shouldn't run your mouth. That's the lesson I've just learned here. 1 over 768 inverted. And then that would give us, wow, yeah, it's quite different. 131.179. So clearly a sample size of 768 should not be considered too large in this case. Okay, so that would mean that N is approximately 132 here. And N is approximately 159. Okay. So yeah, the takeaway there is that 768 for the population size is certainly not too large to have an impact on the calculation, as we can see. So we would have to test to see how big that bound would have to start to get. Yeah, so it's actually very large. So for illustration, so what N would be considered large? Okay, well, in this experiment, when N is approximately 1,000,000, we see agreement in sample size. Calculation, right? So again, going back to one of the points I was making earlier about the use of this formula, when so in our original studies, when we considered when we were working with infinite populations, so like we did at the first and the second year level, it made sense to ignore the 1 over n factor. Here we can see, for example, that when n is only in the range of, well, when it's equal to 768, that makes a big difference on the sample size calculation, because the differences here are roughly 27 units that we need to collect, which is I think would be pretty significant depending on how much funding you have for the study. But how big does n need to be that we can ignore it? Well, for this particular experiment, based off of the variation estimate and the bound we're using, we would need n to be in the range of 1,000,000 in order for us to ignore that bound. So that's, a very, very large population, obviously. All right, so that's our first example of sample size calculation. I'll have to make a little bit of space for the second example, but it's going to be the same idea, except we're using the range to compute sigma hat. So this will be where we stop for quiz 1. So I'll just make a note here. So this will be quiz 1 covers up to here. Okay. So the first quiz will cover everything from lecture set 1, so preliminary definitions, and then lecture set 2, derivate or properties of the estimators of simple random sample, properties of the simple random sample estimators, application of the simple random sample estimators, coefficient of variation, and sample size calculation. Okay, so I think that's a pretty fair first quiz. And again, so if you guys can just send me an email over the next week and kind of just let me know where, if I don't hear from you, I'll just assume that you're okay with writing in the classroom. But if, if you want to chat about other options, just send me an email and let me know your comfort level and we can try and work something out, okay? Otherwise, anyone that has accommodation through ARD, I'll email you directly and let you know how we're gonna handle that. And
So no office hour today?
that's correct. No office hour today. And I think that's it. So assignment 1 due this evening. I'll make a quick update to assignment 2, but that's also posted. And otherwise, if you have any questions, let me know. And I'll talk to you guys on Wednesday, and I'll let you know the details for Wednesday. But again, like all lectures, I'm going to try and make the exact same effort in terms of online communication. So regardless of where I'm located, you can make your own decision about how you want to attend. Okay, so have a good couple days. Sorry for running a little late, and I'll talk to you guys on Wednesday morning.
So the J always becomes